Okay, in the recent lectures, we've been talking about the factors. Well, first of all, the quantities that describe specificity, and then the molecular factors that give rise to it. Let's look at a few examples, especially in the context of DNA protein recognition. The reason for this is that DNA is rather easier to talk about. It has a smaller range of possibilities than proteins do, and so it's a pretty decent class of molecules that we can talk about under one rubric rather than talking about 1,000 different special cases. So these kinds of things involve transcription factors, complexes of proteins bound to a DNA that initiate transcription or suppress it for that matter, repair enzyme binding sites, so you've got a DNA that's got some damage to it or some other kind of problem, and enzymes have to find that site and bind to it. Yeah, replication start sites often on a genome. There's only one place on the whole genome where you can start replication and have it work. Restriction enzymes, yeah, very small numbers of sites where you can get a cut and so on. All of these are situations where there's only one site per cell, and therefore very high specificity is needed. Let's see how that works on a molecular level. What kinds of patterns are we looking at, right? Getting specificity requires some kind of pattern matching or pattern complementarity. What sort of patterns actually are on these molecules, and what kinds of things drive the binding in the first place? So let's talk about how DNA is built, just to remind ourselves. I think probably everybody has seen this kind of stuff before, but maybe not the kinds of features that we need for this particular case. So let's go over them. DNA is, of course, double-stranded. There's a strand that's got a sequence that's called the sense strand. There's a strand that's got a sequence that's called the antisense strand. The two of them are wound around each other in a double helix. There's a backbone on the DNA that consists of alternating sugars and phosphate groups. The phosphates all have a minus sign, so there's a very high charge density, negative charge density on DNA, and that's really important and relevant for binding, of course. It means that unlike proteins, well, that compared to proteins, DNAs are extremely highly charged, and that, of course, is going to affect how things bind to it and what kinds of things bind to it. Then attached to each of the sugars is a base of some kind, and then the bases on the opposite strands are hydrogen bonded to each other. And that's, of course, a type of molecular recognition, an internal type of molecular recognition. And we won't talk about that too much because I think it's pretty obvious and everybody understands it, but it is an example where hydrogen bonding plays a role in the specificity. Of course, the binding of one DNA to another is really specific, or can be really specific. It's sequence complementarity, right, or hybridization. The sequence on one strand has to be complementary to the sequence on the other strand in order for the two strands to come together and form a duplex. And that sequence specificity is pretty much entirely due to these hydrogen bonds. On the other hand, the hydrogen bonds don't contribute very much to the stability or to the binding of one DNA strand to another. The thing that actually drives thermodynamically the binding itself are the stacking interactions, which is a type of hydrophobic effect. The bases are relatively hydrophobic compared to the backbone, and a type of nonpolar interaction, or van der Waals, or induced dipole kind of interaction due to the fact that the bases are all aromatic. So it's these relatively non-specific stacking interactions that actually provide most of the delta G that drives double strand formation. But it's the hydrogen bonds that actually determine the specificity of the interaction. And again, that's a typical kind of pattern. Hydrophobic interactions, or the hydrophobic effect, driving binding, and hydrogen bonds and other kinds of patterns determining specificity. Let's see, yes, here's just an example of that again, and an example of things I've already said many times. Here's a fraying closing reaction. So going this way, the end of the DNA frays, as it's called, which means one or two of the end base pairs opens up. And when it opens up, it gets exposed to water, and then all of the hydrogen bonds that would normally be bound to each other, to the other bases in the base pair, become hydrogen bonded instead to water. And you can see that, in fact, once the base is exposed to water, there's a whole lot more hydrogen bonding sites. There's a lot more than 3 in the final open state than there was in the closed state. And so even though each of these hydrogen bonds, even each of these water hydrogen bonds, is weaker than the hydrogen bonds within the base pair, yeah, the net hydrogen bonding, well, it turns out that the net hydrogen bonding interaction is still favorable when you close the base pair. It's just not very favorable. It's only weakly favorable. And so, yes, the hydrogen bonds do help hold the duplex together, but the main interaction, or the main hydrogen, the main driving force is the stacking rather than the hydrogen bond formation. All right. The DNA also, each DNA base pair kind of looks like this. It's not just a straight, across thing with a sugar over here and a sugar over here and the bases in between. It's kind of a, what's the word? I don't know. It's kind of a bent thing or a curved thing. And what that means is that when the bases stack on each other, if they stack in a way that the bases are kind of going across the center axis of the double helix, then the sugars are a little off center, right? If this is the center line for the helix, then the bases are a little off center. And that's true as you go down the helix. Every single center line goes through the bases, but the sugars are a little off center. And what that means is that when you form the double helix, there's the 2 grooves that you get in the double helix. This one and this one are of different sizes. And they're called the major groove, that's this one, the big one, and also the minor groove, which is this little one. And so on a space-filling representation of the molecule, it looks something like this. You can see the major groove is a lot bigger than the minor groove, and that has lots of implications for specificity, because if you're going to read the sequence of the DNA, in other words, if you're going to bind a protein that binds only to a specific sequence site, you got to be able to see what the sequence is. You got to be able to see the bases, that is. And that's kind of hard to do in the minor groove. The minor groove is narrow enough that it's kind of hard to see what the sequence is in the minor groove. It's much easier to see what the sequence is in the major groove. And so when proteins come along that bind to specific, don't just bind non-specifically anywhere on the DNA, but bind to specific sequences on the DNA, they tend to look at the bases in the major groove. Here's just a little bit more on that. And let me say that this type of DNA is called bDNA. There are other kinds of DNA. We'll look at something called aDNA, or RNA for that matter. And there are other kinds. There are C and D and Z DNA, other conformations of the DNA, but we won't talk about these. We'll just talk about B and D and aDNA, and we'll contrast these to B and A as a sort of way of understanding what these other ones would look like if we were going to look at them. The Z-DNA is actually left-handed, so this is a right-handed double helix. Z-DNA is actually twisted the other way, so that's a really weird one. But anyway, we won't talk about all those things. All right, so this is bDNA. It has a pretty wide major groove, 15 angstroms, and if you look at a space-filling model, yeah, you can see the base edges, right? And those base edges, as we'll see down here, down there, actually contain enough information on them, enough structural or sort of pattern site detail on them so that you can tell what kind of base pair this one is, what kind of base pair that one is, what kind of base pair that one is by looking at, say, hydrogen bonding sites and other kind of sites on the edges of the DNA. So it's possible to read the sequence by looking at the edges of the DNA. On the other hand, if you look at the narrow groove here, the minor groove, here it is, then yeah, you can kind of still see the edges of the bases, but they're much more deeply buried. This backbone of this sugar phosphate backbone is actually pretty big. If you look at it on this stick model representation, it looks pretty small and it looks like the bases are pretty accessible, but when you look at it in a space-filling representation like this, where the sizes of the atoms are actually represented as they really are, or closer to what they really are, then this backbone's a pretty thick, heavy rope. And in the narrow groove, it mostly blocks access to the bases. I mean, it doesn't block it entirely. Protein side chains, amino acid side chains can still get into this thing and still look at these edges a little bit. But it's much more restricted, much harder to get in there than it would be for the major groove. All right, what about those edges? What about the edges of the base pairs? What kind of ways can we use to recognize them? Well, you can't see the flat surface, right? They're all stacked, they're hidden, they're buried. What you can see is these edges. And so what you're looking for is interaction sites along those edges and a pattern of interaction sites that can be used to identify them. So if you look in the major groove side, so there's a major groove side for every base pair, there's a minor groove side for every base pair. And if you look at the major groove side, you can see, yes, this is an acceptor, an H-bond acceptor, another H-bond acceptor, an H-bond donor, and then a hydrophobic site, really. It's called a hydrogen atom site here, down here in this key. But what that amounts to is something that's a little bit more hydrophobic. You can see this part of the molecule here doesn't have anything obviously polar, so it's a little bit more hydrophobic. So this is a hydrophobic area. And you can see the pattern here is acceptor, acceptor, donor, hydrophobic. But if you look, and that's for a GC base pair, but if you look at a CG base pair, just flip things around, then it's hydrophobic minor, hydrophobic donor, right, acceptor, acceptor. It's the opposite pattern. And if you look at an AT base pair, then it's, yes, acceptor, donor, acceptor, hydrophobic. And if you look at the TA base pair, then it's hydrophobic, acceptor, donor, acceptor. So a different pattern depending on which of the four possibilities you're seeing, a GC base pair, a CG base pair, an AT base pair, or a TA base pair. And that means you can, in principle, if you've got the right kinds of interactions, you can, in principle, read the sequence by looking just at the major groove alone, or the minor groove alone, or looking at both of them, of course, gives you still more information. All right, here's the difference now between A-form and B-form DNA conformations of DNA. I mentioned this below or above, but let's look at it a little more closely. This is B-form DNA, which is something close to what most natural, normal DNA exists in if it's not under strain, if it's not under unusual solution conditions in a cell. It's mostly, the conformation varies as you move along the DNA. It's not static, but it's something pretty close to B form in the vast majority of sort of chromosomal DNA. On the other hand, if you have a double-stranded RNA, double-stranded RNAs are rare in the cells, right? There are some viruses that have double-stranded RNAs in them, for example, as their genome. But mostly you don't get double-stranded RNA. Most RNAs are single-stranded. Messenger RNAs and tRNAs and ribosomal RNAs and all those things are all single-stranded RNAs. So a double-stranded RNA would be unusual. But an RNA-DNA hybrid is not so unusual because that's what exists when for a while at least, when the DNA is being transcribed in order to form a messenger RNA. So RNA-DNA hybrids are in this A form, And it's also possible in principle to, under various relatively weird conditions, to twist or torque an actual DNA into the A form. So just for those of you who haven't heard of a DNA-RNA hybrid before, what that means is that one strand is DNA, and the other strand is RNA. So you got half RNA in your double-stranded molecule, and then it turns out that just having even one strand that's RNA is enough to force the whole thing into something that looks like it's a double-stranded, I mean, conformation-wise, looks like it's a double-stranded RNA. All right, what is different about the RNA, about the A form? Well, it's basically this. If you look down the axis of the molecule, so look this way, for example, down the axis, and look at where the base pairs are, they're no longer over the center, the helix axis of the molecule. They're offset from the helix axis. So there's a big hollow or hole going down the axis, and you can see that in this structure, right? If I look at this thing, this is the minor groove here for A form. It's almost as if it were a sheet or a ribbon that's wrapped around an invisible pole down the center. You can see the sheet wrapping around the pole as you go around. So there's this big hollow down the center. There's this very shallow minor groove, which means the bases are a little bit more exposed in the minor groove in A form than they are in B form. And then this major groove is extremely deep. You've got to go all the way across the helix axis in order to look at the bases in the major groove. Here it is again. Here's the major groove. Here's the minor groove in the ball and stick representation of the molecule. Here's what it looks like in something like a space-filling model. And again, you can see it looks like a ribbon here that's wrapping around an invisible pole in the middle. So it's a quite different, I mean, on sort of a generic level, yeah, they're both double helices. They're both right-handed. There's a lot of similarities between A and B form. But in fact, the A form is really quite different from the B form and has a lot of implications. We'll see that later when we look at protein binding to these things. All right, so if you have a B form, what kinds of protein binding motifs occur? Well, one of the most common ones, probably the most common one, is an alpha helix that binds into the major groove or inserts itself into the major groove, right along the major groove of the DNA. And the alpha helix here that's shown here, this green spiral, is the backbone of the protein, of the amino acid chain. And of course, along the backbone, there are side chains sticking out, the side chains of each amino acid. And those can reach out away from the backbone and make interactions with the DNA. And because these side chains have hydrogen bonding and hydrophobic interactions, they can, in effect, read the pattern of hydrogen bonding and hydrophobic sites on the bases of the major groove and also of the minor groove, and we'll see examples of that. Yeah, I say here also that while in principle, of course, an alpha helix could also bind to the A form, could go into this major groove in the A form, it doesn't fit as well, and it's not as nice a fit as it is for the B form. The B form sort of groove here for the major groove, it fits the alpha helix, the shape and size and other properties of the alpha helix much better in the B form than in the A form. The other thing that's important, so apart from the sort of geometry or shape of the molecule, is, the fact that every phosphate group here has a negative charge under normal pH conditions means that this is a really highly negatively charged molecule. It's got a huge amount of charge, and there's lots of implications for that. We can talk about that. For the packing of the DNA, for lots of other effects, for counter-ion condensation and all kinds of sort of large-scale macroscopic effects due to this charge. And that's shown in this picture. The red here means negative potential. It basically means effectively negative charge. The white areas are places that have equal amounts of negative or positive charge, or no charge at all. Usually no charge at all is what that means. And the blue parts are the positive parts. There are some positive parts on the base edges. Basically, the amine sites on the base edges can be slightly positive. But overwhelmingly, this is one big red molecule, right? It's almost entirely negative. Here's the A form, here's the B form, here's the shallow minor groove, here's the really, wait a second. I guess that's the major groove. Looks different than I expected. Here's the minor groove, and on the B form, the major groove is obvious, the minor groove is obvious. All right, so anything that's going to bind this has got to account for that negative charge. Let me say also that while I'm showing this picture shows the DNA molecule alone, in any kind of solution, there's a bunch of counterions, right? All these phosphates have negative charges. They don't stay negative. They have to have a counterion somewhere near them. There's a counterion atmosphere that's surrounding each of these negative charges. And you got to get those counterions away if you're going to bring in a protein and replace them. And that plays a big role. And so all the things that we said earlier about charge-charge interactions, about electrostatics, it applies in spades to DNA protein binding. So here's an example of that. Here's a particular transcriptional repressor, something that turns off transcription or slows down transcription at least. And so it has to be a DNA binding protein. And you can see, here's the DNA, here's the protein, the color code is the same. Here are positive regions, but in the parts that touch or get close to the DNA, it's solid blue. There's all kinds of effectively countercharges, right? Instead of let's say a sodium ion being a countercharge or a magnesium ion being a counterion, the protein itself has countercharges on it, and that shows up in this blue, as blue here, which are replacing, in effect, the natural solution countercharges that would be there. Yeah, here's something binding to an RNA. And here's another example. You can see lots of blue. And that's generally the rule. There are very few cases that I've ever seen where a protein binds to the DNA and doesn't have this basically solid blue electrostatic potential acting as a counterion to or a countercharge to the DNA. So part of what about the binding energy? Does this contribute to the binding energy or just to the specificity? In other words, is it a matter of charge-charge matching, pattern matching, or is it actually a driving force for causing binding? It probably is in most cases something that contributes to the binding force. But remember, you've got to get these counterions away from the DNA in order to bring the protein in, and that costs you something. This counterion to DNA interaction is also favorable. You got to break all those interactions, and also with the water, or most of the ones with the water anyway, in order to bring this protein in. So the net overall effect, I'm sure it varies a lot from case to case, but the net overall effect probably is fairly favorable for the electrostatic interactions between a positively charged protein and a negatively charged DNA. But most of the interaction is going to basically it's going to be counterbalanced by the need to pull away the solvent. And so what a really negatively charged protein like this mainly means, or one of the things it means, is that this protein is going to have a hard time binding to other proteins, right? It's going to bind pretty much, it's not going to be sequence specific on the DNA. But with this highly negative charge, it's going to be very much more likely to bind to some kind of nucleic acid, DNA or RNA, than it is to another protein. So it contributes in that way to specificity. It doesn't contribute to the sequence specificity, but it does contribute to the specificity between proteins and nucleic acids. All right, let's look then at the ability of a protein to distinguish whether it's an A form DNA that you're binding to or whether it's a B form DNA that you're binding to. Here's a protein, it's called double-stranded RNA B binding domain, DSRB, and it specifically binds to A form. How does it tell A form from B form? Well, it does it by spacing. You can see this part of the protein fits into the minor groove of the A form. Well, it's an A form RNA here, but it could be an A form DNA. And likewise into the minor groove of 1 unit away or 1 turn away on the RNA. And it even fits a little bit here. There's another sort of feature that fits into the minor groove, into the major groove here. And these spacings have to be right. They have to match between the nucleic acid here, the RNA, and the protein, or else you're going to get a bad mismatch, and that's what happens on the bDNA over here. The spacing along the helix is different for A RNA or DNA than it is for bDNA. And so look, the same protein coming in and interacting just hits things badly on the DNA, on the B form DNA, than it does on the A form, either DNA or RNA. Also, of course, look at the side chains here. They can reach in and interact with the sequence, so a thing that has a general preference for B form, for A form over B form, also can have a sequence preference if the side chains are lined up right or have the right sequence themselves, amino acid sequence, in order to do that. Yeah, okay. There's some other comments that I could make here, but let me not bother with that. Here's an example of actual sequence specificity, and this is now on B form DNA. So notice, first of all, there's 2 subunits. Why 2? Well, you could just get away with 1, but if you've got 2, then you're going to get twice as much specificity, right? Because not only do you have to get a match here, you got to get a match over there, and the spacing between these 2 subunits has to be right in order to match the spacing along a B form DNA versus an A form, say RNA or DNA. And notice, yes, the alpha helices are reaching down into the major groove of the DNA, just as we talked about before. And the side chains that are attached to those alpha helices, here they are, looking more closely, are reaching down and touching the base edges, just as we sort of theoretically talked about above. And those side chains are, in fact, are capable of, in fact, and in this case actually do, read the sequence so that this protein, in both of its binding sites here, both of its binding locales here, will bind only or bind very strongly, preferentially, very specifically to one particular sequence on the DNA, and it finds that sequence by reading the base edges, mainly in the major groove, but we'll see that it actually also reads a little bit in the minor groove as well. Here's some of the interactions that amount to reading the base edges. A glutamine comes in, it can form 2 hydrogen bonds with the edge of an A base. A leucine comes in, so a glutamine has hydrogen bonding sites, donors and acceptors that match, right? Here is, yes, this is an acceptor over here, this is a donor here, this is a donor here, and this is an acceptor over on this side. So it's a donor-acceptor pattern that matches between the glutamine and the A base on the nucleic acid. In the case of a leucine, very hydrophobic, right, a purely hydrocarbon side chain, can interact favorably via hydrophobic effect with the methyl group on a thymine. And so this is a matter of looking, or this is an example of looking at a pattern that part of the pattern is the hydrophobicity, the hydrophobic patches on the base edges as well. And so hydrophobic amino acids can help read out the hydrophobic parts on a base edge. And again, here's another example of the hydrogen bonding pattern, an arginine hydrogen bonding to a G residue. Again, this is a donor, acceptor pattern, a different pattern than the one up here, but still resulting in two hydrogen bonds, and therefore the ability to distinguish a G from an A when reading along the base edges. All right, so this is the general pattern, maybe the most common type of pattern that allows a protein to bind to a specific site on the DNA, one specific site in the whole cell along the DNA. There is another kind, and this is called direct readout of the sequence. But there's also an indirect readout of the sequence, and that's more subtle and a little less specific, but still is used. And indirect readout depends on the fact that the flexibility, the ability of the DNA to bend itself, also depends on sequence. Strings of AT base pairs, for example, have a different flexibility than strings of GC base pairs, and other kinds of sequences also have different flexibilities. And that means that if you have a protein like this one that requires that the DNA bend in order to bind to it, right? If the DNA were not bent here, it couldn't make interaction with this surface or this surface, and so wouldn't be able to take advantage of the full binding surface, the full binding interaction, the full delta G of interaction. But it can if it bends, but that's only going to be possible if it doesn't cost too much energy to cause this bend, right? The bending itself costs energy. And so the question is, how hard is it to bend the DNA? And that depends on sequence. So you can tell at least something about the sequence of the DNA by whether or not it can even form this rather tight, sharp bend that's necessary to bind to this DNA, and that's called indirect readout. Here's another example of a specific type of motif that often you see in DNA binding proteins called a zinc finger. It's got a zinc 2+ ion, which I'm sure, I don't remember right off the top of my head whether it's known, well, I'm pretty sure it is known, that the zinc 2+ charge interacts favorably with the negative charge. I'm sure it does. It's not quite, they're not quite right next to each other, but they're close enough to interact for sure. And so the zinc 2+ charge helps the binding. But also there are these alpha helices that fit in the grooves. There's more than one of them in a row, so you can get the cooperativity and extra binding strength from two domains rather than just one. And then there are these side chains that come across and can form an especially strong set of interactions. Here's the base pair. Here's the pair of hydrogen bonds that come from an arginine on the zinc finger. And one extra feature that's occurring here that didn't show up in the last example is that this arginine is held in place by another side chain on the protein, right? This is an asparagine that is part of the zinc finger here, part of the protein anyway, and it's hydrogen bonding to the arginine. So there's an internal action within the protein, or interaction within the protein, that's holding this arginine in place so that this arginine can bind better, interact better, more specifically with the edges of the CG base pair. That makes this interaction, this hydrogen bonding interaction, more favorable than it otherwise would. So this hydrogen bonding interaction is helping to make this hydrogen bonding interaction more favorable. All right, yes, this is an example where the thing that inserts itself into the major groove of a bDNA here, a B-form DNA, is not an alpha helix. It's a pair of anti-parallel beta strands that stick themselves in. So it isn't just alpha helices. Other kinds of features can go in there. I'm sure that there are cases where a random, so-called random coil part of the protein also can insert itself into the major or even the minor groove. I mean, almost anything that can happen will happen if you look widely enough throughout the database of the protein data bank, for example, of DNA protein binding structures. And the alpha helix case is the most common one, but there are cases of anti-parallel beta strands like this, which is part of a beta sheet, right? It's a little bit of a beta sheet sticking itself in there. But there are probably also cases which aren't either alpha helices or beta sheets. And once that, in this case, double anti-parallel beta strands stick themselves in, then of course their side chains can dangle off and interact with the edges of the DNA, just like off of the alpha helix case. Let's see. Oh, here's another example of another kind of thing that can happen. In this case, this alpha helix is reading the base edges in the major groove. I think, yeah, it is the major groove. But not because of hydrogen bonding between the side chains and the DNA bases themselves. There's an intervening water. So there's a bridging water that allows this whole hydrogen bonding arrangement to occur. Without the water, this guy wouldn't hydrogen bond to that guy. They're both, let's see, this is an acceptor and this is an acceptor too, but the water has two donors on it, right? So it can bridge between two acceptors and allow a favorable and reasonably strong interaction that allows this particular protein to read the step edges, even though it doesn't have the same pattern that you would expect for reading the step edges. It's reading it via this extra water molecule rather than reading it directly itself. And then finally, this is the Crow protein we looked at earlier before we talked about the interactions that were occurring in the major groove, the side chains coming down and reading the step edges. But that same protein also has a couple of arginines here that are obviously reading the step edges, reading the base edges of the DNA in the minor groove as well. So both minor groove and major groove get read. It's just a lot easier and a lot more common for the reading to take place in the major groove. And that is it for today. We'll talk about cooperativity, chapter 14, or is it chapter 15? Anyway, we'll talk about cooperativity next time. I know the topic, but not the chapter number.